So today will be the final class of properties of matter. We'll complete viscosity. You have properties of matter in your upcoming major test in the next weekend. Okay. So we were discussing about viscosity in laminar flow last time. So in the situation of laminar flow, we saw that if we consider a surface of fluid which is moving at a velocity v, such that its surface area is a, such that there is a velocity gradient in this direction. Let us say dv by dy. Suppose that is a negative quantity. So that means this part is having higher velocity than this part. So the top surface will experience viscous force in this direction. And that viscous force was given by the formula coefficient of viscosity into area into modulus of this velocity gradient. So this was the first situation we see viscosity in. Now we'll see the second situation in which viscosity is there today, where there is viscous force, or what we also call drag force, on a solid object moving inside a viscous fluid. In certain cases, it can even be a fluid moving inside a fluid, for that matter. So, for example, you can have this situation also. For example, raindrops falling through air. There's one fluid body moving through another fluid. Okay. So raindrops falling through air experience air drag. That is nothing but a form of viscous force. Okay, so in general, when a solid object or one object might be even of another fluid, but if an object is moving with a velocity v inside some kind of a viscous fluid, then it experiences a drag force or a viscous force. It's exactly opposite in direction. So the magnitude of this drag force is proportional to the speed. The magnitude of this drag force is also proportional to the coefficient of viscosity between the two objects. And in general, this is the equation. Or if we write it as a vector equation, we'll write it as minus of, because it's in opposite direction. Okay. So C is a constant which has dimension of force divided by coefficient of viscosity into velocity. So remember, coefficient of viscosity had dimension of force per unit area into time. And this was length per unit time. So this becomes of the dimension of length. So this constant has the dimension of length and depends on the shape and size of the object. So usually for different kind of shapes of objects, it is experimentally determined. There's constant of proportionality over here. But of course, as you know, Stokes' law gives you the value of C for a special type of object, which is a spherical solid object moving inside a viscous fluid. So we'll come back to that. Okay. Remember, coefficient of viscosity we discussed last time. It is expressed in poise or Pascal second. It has the dimension of Newton second per meter square, or the unit of Newton second per meter square. So I'll just pause for a moment. You can just go through this section. We'll discuss further next. So this is directly, I'm continuing from where we left off last time, which was viscous force in the case of laminar flow. And we had seen that example problem also. So that was viscous force in the case of laminar flow. Now we come to the second situation in which we observe viscosity. Which is in this situation. It acts on a solid object moving inside a viscous fluid. So we'll see further that this drag force is again a non-conservative, dissipative kind of force. It's quite easy to prove that it's non-conservative. Because it's easy to show that in a round trip, the work done will be non-zero. In fact, negative. Always ends up doing negative work on the object it acts on. So it's a dissipative drag force. Delivers negative power. Now, the physical conditions on which the magnitude and direction of force depend. The direction of force is always opposite to the direction of velocity. And the magnitude of the force is proportional to the speed with which the object is moving, as well as proportional to the coefficient of viscosity, and also proportional to another factor, which has the dimension of length and depends on the shape and size of the object.
Sir, what's that after dissipates? What energy is that?
Sorry, come again.
Sir, what is that after dissipates energy? What is the energy there?
It dissipates mechanical energy.
Okay.
Kinetic energy or mechanical energy. It always ends up dissipating it because it does negative work. It's easy to understand why it does negative work because it's acting opposite to the velocity in direction. So the power delivered, dot product of force and velocity, will always be negative. Just like kinetic friction in that sense, that also does negative work. But the difference is kinetic friction is independent of the speed with which the object is moving or the relative speed. It only depends on the magnitude of kinetic friction, only depends on coefficient of friction and the normal contact force. Here, the magnitude of the drag force also depends on the relative speed because the object is moving inside the fluid. The faster the object is moving, the larger the drag force becomes. Okay, so now we will see the next we'll see the special case of drag force on a spherical object and Stokes law. So obviously we are talking about a spherical body moving inside a viscous fluid. So it need not be a solid sphere, it can be a hollow sphere also. Just the important thing is that the shape, the outer surface is spherical. Because the outer surface is what interacts with the fluid around it. Okay. So if this is, for example, moving with a velocity v, this will experience a drag force because of the liquid or the fluid around it, which will be exactly opposite as a vector in direction. So this is our viscous fluid. In the case of a sphere of radius, let's say capital R, the viscous force magnitude is given by, or the drag force magnitude is given by, as you might have known, 6 pi into coefficient of viscosity into radius into V. This bracket is just to show that this is proportionality with respect to V. Or if we write this as a vector equation, the drag force is minus 6 pi eta R V vector. So that constant that we were talking about earlier, over here, this is 6 pi R. And this is from experimental data again. There is no theoretical way to prove this. This comes from experimental analysis. Okay, so the other aspect that we studied from here is the terminal velocity condition. And in general, the free fall of a solid sphere inside a viscous fluid. So the moment we're talking about this solid spherical body moving inside a viscous fluid in free fall because of gravity, apart from gravitational force and buoyant force, there is the third factor of viscous force or drag force. And because the drag force goes on increasing as the speed of the object increases, so eventually it achieves a situation where the forces balance and it achieves a terminal or a final velocity in which it is in what we call dynamic equilibrium. That is, it is moving but with zero acceleration. So the net force on it is zero. So that velocity at which that happens is called the terminal velocity. So we'll understand the entire dynamics of what happens when, let's say, a solid spherical body starts from rest and it starts falling under the action of gravity inside a viscous fluid, how its velocity behaves with respect to time before it finally becomes a constant or a terminal value or steady value, you can say. We'll look at that aspect next. So let's say at time t equal to 0, we have just released from rest a solid spherical body. It's made of homogeneous material or isotropic material, so it has a uniform density. So this is a solid sphere of radius, say r, and density of that solid, uniform density is rho s. So mass m is density of the solid into 4 by 3 pi r cube. Okay. Now this solid sphere is released from rest at time t equal to 0. So that's when we start our clock, and the initial speed is 0. And this is located inside a viscous fluid with gravity acting downwards like this. So immediately at t equal to 0, it experiences two forces. It experiences weight, which is pulling it down, and it experiences obviously buoyancy. But it does not experience any viscous force at the moment because the velocity is 0. So the action of these two is to give it a downward acceleration of a naught, let's say. So at t equal to 0, the initial velocity is 0, so the drag force is 0. Okay. So let's say the fluid, it has a density of rho L, and it has a coefficient of viscosity of eta. Okay. So at t equal to 0, only weight and buoyant force is acting. So mg minus buoyant force is equal to mass into acceleration. Okay. B is of course buoyant force. So mg will become density of the solid multiplied by its volume. So isotropic solid sphere. Buoyant force will be weight of liquid displaced, so density of liquid into same volume to g. Okay. So this is equal to mass into acceleration, where m is again this quantity. Okay. So you'll see that the initial acceleration comes out to be 1 minus the ratio of the density of the liquid to the density of the solid into g. This is the initial acceleration. And we'll realize in a bit that this is also the maximum acceleration it has during its motion. So this is the initial acceleration at time t equal to 0. Now, if we compare this to a little bit of time later, by the time, let's say, the object has descended vertically up to this point. So by now, it's picked up a velocity v. So its acceleration a would have become less because of the additional force of drag force or viscosity which is acting on it. So there is buoyant force still acting. There is mg still acting, the gravitational pull of the earth. These are invariant forces. They don't change according to how the object is moving. But as the object picks up more and more velocity, there is a stronger and stronger amount of drag force which is active. This is at t equal to t. You can see that the acceleration has become less than the initial acceleration already. Okay, assuming it's not become zero yet. So now at a general time t equal to t, we can see that mg minus buoyant force minus the drag force, that is equal to mass into acceleration. Now here the drag force will be how much? It will be according to Stokes law, 6 pi eta into radius into v. So just note down this part and then we'll see how the acceleration varies according to the speed of the object as it's moving. And then using calculus, we can predict what type of profile of velocity it has, how the velocity is changing with time, etc. Okay, so once we substitute the values of these forces, you can see it's really become a kinematics problem of variable acceleration. So we have to use calculus. So before that, of course, substitute these things. So mg minus buoyant force is equal to again that density of solid minus density of liquid into 4 by volume into g. Okay, the drag force is 6 pi eta r into v, and that is equal to m, which is again density of the solid into 4 by 3 pi r cube into e. Just tidying this up a little, we can see that we get acceleration as this divided by this, which you will see is actually our a naught minus some factor I'll write as beta into v to get this relation, or dv by dt is equal to the initial acceleration minus a factor into v, where a naught we have just seen above is 1 minus relative density of the liquid with respect to the solid into g, and this factor beta will actually be 6 pi eta r divided by the mass. So this will become 9 by 2 eta upon r square into density of the solid. So now basically we have to solve this dynamical equation to understand its motion completely. Of course, the motion is one dimensional, it's a straight line motion, but how the velocity changes with time, how therefore displacement will be varying with time, etc. Okay, now one more thing we'll understand logically, that provided it has enough space and doesn't hit the bottom floor or whatever of the container in which the liquid is there and all that. So assuming it has a sufficiently large displacement to make before it reaches the sort of conclusion of its journey, it should reach a condition somewhere where the acceleration becomes zero, because the drag force is continuously increasing. Or you can see that from this also you can see that A is decreasing as B increases. Therefore, at some stage, which is called the terminal condition, okay, acceleration becomes zero and v equal to that terminal velocity becomes constant. So it reaches some stage, and at that stage, whatever velocity it has, from that point onwards, the velocity does not change. So from this itself, can understand that when v becomes the terminal velocity, acceleration should be 0. So the terminal velocity is value is this factor, which when you do the calculation will come out to be 2 by 9 into density of solid minus density of the liquid into r square into g divided by eta. So this is actually a formula that you're supposed to know by heart, but you don't need to actually memorize it as a formula. What you can just do is remember it as a concept, that in the terminal velocity condition, this is what happens. At the terminal velocity condition, the acceleration becomes 0. You can even remember it this way. So net force is 0. So mg minus buoyant force minus drag force should become 0. So like the apparent weight should be balanced by the drag force. So it's very easy to generate this formula from this. Difference of densities into volume is equal to 6 pi eta r into that velocity in the terminal condition. So this is very easily going to give us the same thing. So you really don't have to memorize any formula over here. You can just, the only formula to memorize is the Stokes law formula, that viscous force on a spherical body is 6 pi eta r into v. Okay, so this is the terminal velocity formula. Now, the next thing here, you want to solve velocity as a function of time. As it starts from rest and all that. So remember we had that equation that the rate of change of velocity or the acceleration was a naught minus beta v at any given instant, where a naught was of course this factor, initial acceleration, and beta was this kind of factor, 9 eta divided by 2r square. This kind of factor. Also that a naught upon beta was equal to the terminal velocity. So we have that. So this now has to be solved as a function of time. I mean, this has to be integrated to solve v as a function of time. So we'll integrate this, and also it started from rest. So we can solve the integral on both sides by taking limits initial condition to instantaneous velocity can be the upper limit. So this will give us minus of natural log, or minus of 1 by beta, natural log of a naught minus beta v. On this, the limits v equal to 0 to v equal to v. On the other side, t limit 0 to, okay. Because as you know, integration of 1 by x is ln x. So integration of 1 upon any linear function is 1 upon the coefficient of x into natural log of that linear function. Okay. So now you put the limits and solve for v. And finally, after putting the limits, you have to take exponential also. So 1 by beta minus of ln a naught minus beta v, minus of minus will become plus ln a naught, become t. So a naught upon a naught minus beta v will become e raised power beta into t. So you can just invert this. So beta t. You get this relation. Just check out the steps in between from here to here. Okay, so now what you notice in this is that this factor A naught upon beta is actually the terminal velocity, which we had seen was that formula 2 by 9, that r square g factor. So, and this factor beta, which is, we have written the value above, it has the dimension of time inverse. So we can take beta as a factor like this, where tau is a constant having the dimension of time. It is given by 1 by beta. Yeah, so 2 by 9 r square into density divided by eta. So there's no g in this. So this tau is a constant with the dimension of time. So using this notation here, that beta is 1 upon tau, and this factor a naught by beta is the terminal velocity. We can see that the velocity as a function of time is this sort of a function, where this is the terminal velocity, and we can think of tau like what is called a time constant, because it is a constant which has dimension of time and depends on all the properties of the system. It depends on
So
coefficient of.
what was the need to
Sorry, Peter, what's the question again?
so what was the need to define tau?
I'll tell you, no, just note down up to here first, because it has a special significance, this time constant. So for example, if you have a system whose time constant's value is in seconds, then the values of eta r and that density of the solid, etc., is such that the value of time constant is in seconds, then the amount of time it takes to reach terminal velocity will have the order of magnitude of seconds. But for example, if the time constant has a value which is much larger in minutes or something, then such an object or such a system with the object following will take a lot longer to reach the terminal velocity. Okay, so it has a special significance, the value of that time constant tau. Yeah, Vinith, I will scroll up after people have written down this part, so you can. Okay, so now we will observe the significance of this time constant part. You asking why we need to write this separately. So you will see why exactly actually. So first of all, you can see that this expression is such that at t equal to 0, you can see v is becoming 0 because e raised power 0 is 1 and all that also. Whereas as t tends to infinity, now this is actually a little misleading. It's not that it's infinite time. It's more like when t by tau is large, is very large compared to 1 basically. So what happens is e raised power minus t by tau becomes very small compared to 1. Okay. So 1 minus e raised power minus t by tau, this whole factor tends to become 1. So while we write it like this that t tends to infinity, but it actually implies this. Implies this condition over here. So v becomes terminal velocity. So also if we do a graphical representation, it will start making sense to us. The instantaneous velocity here, it follows what we call an exponential path, which goes to become an asymptote. You must have studied the term asymptote by now in mathematics, right? So you'll understand what we mean by this. So this graph effectively asymptotically approaches this horizontal line of the terminal velocity. But practically what happens is that, if like this is the value of time in one time constant, then, so for example, at t equal to one time constant, value of the time constant, tau, the value of v becomes this. So you'll see that when you put the value of e as approximately 2.7 and all that, you get the value of the velocity as nearly 0.63 or 633% of the terminal velocity. So that is the significance of this time constant, that it tells you it effectively tells you how fast it is able to approach the terminal condition. Okay, because you see that at t equal to something like 10 times tau, your v will become very nearly equal to terminal velocity. If you do the calculation, that 1 upon e to the power 10 is such a small number, it will hardly matter. Now, similarly, if you want to talk about the acceleration as a function of time, so doing the time derivative of this factor, so that will become like this. Okay, and is that initial acceleration. You can see that now the acceleration has the behavior of exponential decay. So this is an exponential graph that grows to, you can say, asymptotically approach v equal to terminal velocity. And the acceleration, on the other hand, will decay. This will have an exponential decay. Now, again, the time constant has that significance of telling us how fast or comparatively how slowly this decay process happens. So here also we'll see that time constant has a special significance. At one time constant, the value of acceleration is that is approximately 0.37 of k0. So it decays to about 37% of the initial value within one time constant. So once again, you can see that within few time constants like 9 or 10 or 11 time constants, for all practical purposes, the acceleration is zero. Maths might be telling you that no, it's not non-zero. It will approach zero as time tends to infinity. But practically, from a physics point of view, the acceleration is so small you won't be able to measure it. There is no device which has a least count that is so small. So it's something that's on your instrumentation or your measurement. It's going to show up as zero only. So practically speaking, it's going to be zero. Okay, so I hope it is clear the significance of all these constants over here, like the time constant, the terminal velocities value, right? The initial acceleration a naught. And it's important to understand what they come from, like which one depends on or how each of them depend on the other factors, the viscosity coefficient, radius, things like that. Okay, so there are certain types of questions which are really based more on this kinematics part or this equation of motion part rather than viscosity so much. Okay, for example, we have something like this: a solid object is dropped from rest inside a viscous fluid. Okay, at time t equal to 0. At t equal to, let's say, 2 minutes, its velocity is, let us say, 15 meters per second, and a very long time later, like let's say it's in free fall for several minutes. Little unlikely situation, but let's imagine something like that. Okay, its velocity is 45 meters per second. Okay, or let's make this slightly easier question. Let's take it exactly double. So first of all, calculate its velocity as a function of time. Okay. Find the value of its velocity at t equal to 4 minutes, t equal to 6 minutes, and t equal to 8 minutes. And find its acceleration. G is of course 10 meters per second square. At t equal to 0, t equal to 4 minutes. That is several minutes later. So you can see very minimal information given over here. You don't even know that it's a spherical body. Okay, but nonetheless, it's given to you that it's dropped inside a viscous fluid for vertical free fall. Okay. That kind of situation. So see how we'll make use of the properties of this kind of a system and the equations that we have developed in the previous section. So anybody got the answer for the velocity as a function of time, or at least the time constant or anything like that? Okay, okay. people. I'm working out the values, people. Okay, so here, see what's happening is that irrespective of the shape of the object, okay, we understand that buoyant force mg, and at some point of time, if the velocity is v, some kind of drag force will act like this, where mg minus buoyant force minus drag force is equal to mdv by dt. So this is a constant. Okay, this is a constant into velocity. So ultimately, we'll get this kind of equation that dv by dt will be equal to some terminal velocity into 1 minus e raised power minus t by tau. The formula of terminal velocity might be different if the shape is not a sphere, but ultimately the relationship will be of this type, that dv by dt will be equal to some constant, which is basically a naught minus another constant beta, which is equal to, where a naught is basically this thing, and drag force will be some constant into coefficient of viscosity into v. So that beta factor will be like this. So this kind of thing is there. So now what we have to do is we have to fit this equation that we have, this equation. So this is only telling us that this is happening. So we know that, okay. So this equation has to be fit into the data, that v is equal to 30 meters per second at t equal to 2 minutes. So that means, oh, sorry, not dv by dt, v is, dv by dt is the equation below. Okay. Okay, so this is telling me that 30 is equal to some terminal velocity into 1 minus e raised power minus of 2 minutes divided by some time constant.
So
So
30
tau
is
here
at
is,
the long time. At 2 is 15.
30 is at the long time. Okay, so it's 15, right? Okay. Okay, sorry. So this is correct now. Whereas v is becoming 30 meters per second at t being very much larger compared to 2 minutes. So we'll take it as t tending to infinity, basically, or t by tau being very small compared to 1. So this basically tells me that 30 is equal to terminal velocity into 1 minus e raised power minus of a very large value. So this kind of thing. So t by tau is very large compared to 1. Okay, so terminal velocity is equal to 30 meters per second. That is one information that I get. So now the only thing unknown for me is the value of tau. Then rest of the things I can work out from there. No? So now substitute this terminal velocity in this equation. So we can get the value of the time constant. So 15 is equal to 30 into 1 minus e raised power minus t by tau. So you can see that 1 minus e raised power minus t by tau is half. That means e raised power minus t by tau is half. That means e raised power t by tau is 2. That means t by tau is ln2, which means that this so-called time constant tau is, I mean, this time is 2 minutes actually. So this is for t equal to 2 minutes. This value here. So this is 2 minutes divided by ln2, or nearly 3 minutes. You see the time constant is going on. Okay. So now that we have got this, now the rest of the things are very simple to answer. Okay. So we have got velocity as a function of time because we know the value of the time constant and the terminal velocity. So the first part's answer becomes like this. v is equal to terminal velocity 1 minus e raised power minus t by tau, where the numerical value of terminal velocity we now know is 30 meters per second, and this time constant tau is 2 divided by 0.693 minutes, or nearly 3 minutes. Calculate approximate values. Okay, so that's done, the first parts. Okay. Now we have to find the velocity at all these different times. So I don't know if you solved it, but I think what you should be getting here will be 15 and 30, thana? So 15 and 7.5. So this should be 22.5 meters per second. Okay. Then another 3.75. So that will become 20. 6.25 if I'm not mistaken. At 8 seconds, become another something like this. I think we will get. Just check the values. It's quite easy to show that these are the exact values you will get. And what I'm trying to bring to attention here is that it has an interesting property, that log function or that exponential function. It has an interesting property. We'll also find the acceleration from a different relationship. Okay, we understand that from here, if you differentiate, dv by dt. So as a function of time, so at t equal to 0, the value of acceleration will be actually terminal velocity divided by time constant. So this will also lead you to the conclusion that the initial acceleration itself was very slow, which is probably because the density of the liquid was pretty close to the density of the solid. So its apparent weight is very less. Its initial acceleration is going to be a very small factor of g. So we'll come to that also. So interestingly, you'll see that in this question, we can also find the value of this thing, that what is the density of the solid relative to the density of the liquid or vice versa. You can find that out, assuming that it's a solid object which is homogeneous or it has isotropic density. So just try to calculate the values and see if you're getting them. Oh yes, very good. Aman, you got the same answer for the second part. Very good. So this kind of exponential relationship is pretty important in physics. It comes in a number of places, not just here. I think if you've finished with electrostatics and you're moving towards capacitors, you will be coming to a topic called charging circuits with capacitors and resistors. You'll see there also you have these kind of exponential relationships. Because there it's between charge and time, here it's between velocity and time. Okay, so we've got this time constant and all this. Now you can see that the velocity is terminal velocity into 1 minus e raised power minus t by tau. So the acceleration is going to come by differentiation to be of this type, where you can see that the value of a naught will be the terminal velocity divided by the time constant. So the terminal velocity was 30 meters per second. The time constant was nearly 3 minutes. So I'll take this as, so as you can see, I told you that it's a very minuscule amount of acceleration, which means that the buoyant force was pretty close to the weight. So the initial acceleration, remember, is always mg minus buoyant force divided by m. So assuming an isotropic solid object, the density of the solid with respect to the density of the liquid is basically like this. To invert this relation, you have, or this relation is like this, that 1 minus density of liquid divided by the density of solid is a naught by g. So that's nearly 1 by 60. Okay, so density of the solid with respect to the density of the liquid is nearly only marginally greater. They're almost of the same density. So that's why, in fact, it's taking like minutes to reach the terminal velocity. Watch, I have to show you the calculation of the second part also. So this was the third part, I think, right? Second part's calculation will come like this, that so tau is actually 2 minutes divided by ln2. Let's think of it like this. Okay. Or we know that e raised power minus of 2 by tau was a factor of half. Keep this thing in mind. Okay. So now at t equal to 4 minutes, v will become 30 into 1 minus e raised power minus 4 by tau. So that is 30 into 1 minus e raised power minus 2 by tau squared. No? So that's how you get this relation. So it's reached 3/4 of that velocity. So 22.5. Then similarly, when you come to t equal to 6 minutes, you will see that v becomes 1 minus e raised power minus 2 by tau cube. Okay. So it's become 1 minus 1/8 or 7/8 of 30. That's how we got that value. What was it now? 26.25. And like that, at t equal to 8 minutes, that is 4 times 2 minutes now. So v will become the terminal velocity into 1 minus half to the power 4. That was our 28.75. That also shows you that, if you think of this like a series now, so at some general time, which is some factor n into 2 minutes, the terminal velocity, the velocity would have become the terminal velocity into 1 minus 1 by 2 to the power n. So you can see that it never truly becomes the terminal velocity, but at the same time, the moment n is like, something like 5, 6 or 7, it's practically speaking equal to the terminal velocity. The difference is not going to count too much. Okay. Also, if you think, graphically, it has a very interesting implication. So your terminal velocity was 30 meters per second, and it reached half of that terminal velocity of 15 meters per second in a time of 2 minutes. So what will happen is in the next 2 minutes, this gap will be halved. That's how it reaches 3/4. Okay. Then in the next 2 minutes, this gap is halved. So it reaches 7/8. So in equal intervals of time, actually, this kind of thing happens. Okay, so it goes from, half of terminal velocity to 3/4, 7/8 to 15/16, like that. And same kind of thing you will see for the acceleration also. Look at the acceleration versus time graph. Here, of course, the initial acceleration itself is pretty small, okay, but nonetheless, this will also become half of its initial value in 2 minutes, because that factor of e raised by t by tau is equal to half now. So at 4 minutes, it will become 1/4. This will follow that proper geometric progression. At 6 minutes, it will become 1/8. So at t equal to this kind of thing, the acceleration will become a naught into 1 by 2 to the power n. So many times in JEE, this type of calculation has been minutely tested. Whether it's a question in the form of a kinematics problem where it's given to you that an object starts from rest with an acceleration which is decaying with respect to velocity linearly, something like that. In chemical kinetics, you have this kind of thing: rate of a reaction if it depends on the amount of substance. First order kinetics. I don't know if you've done chemical kinetics. Like, I'm completely out of touch with chemistry now, but okay. So people hope this question is clear fully. Now we'll move on to the very last thing in viscosity, which is again we are back to laminar flow, but it's a slightly different kind of situation. So we will study something called Poiseuille's equation. Don't know if my spelling is correct. I always make a mistake in this. It gives us the laminar flow, the condition for laminar flow of a viscous fluid through a cylindrical pipe. So what this does is this as an equation, it tells us that if, for example, this is a section of a cylindrical pipe, it need not be the full cylindrical pipeline itself. And some kind of viscous fluid is in flow through it. So if it is a viscous fluid, then it will not have at any area of cross section, it will not have uniform velocity at all points. Instead, it will have a, so if I consider a cross sectional area like this, so this cylinder is of radius r and length is L. So first of all, we will see that there is a what we call a radial velocity gradient. The velocity will be maximum at the central axis, and it will follow this kind of a radial profile, that with radial distance from the central axis, the velocity will be decreasing. And we'll also show how it will be decreasing actually. Okay, so velocity will have a radial gradient. So dv by dr will be a radial velocity. There will be a radial velocity gradient. So that's assuming that a viscous fluid is in flow through this. Okay, and to keep the viscous fluid in flow, we'll have to maintain a pressure difference across this. So if this point is A and this point is B, across it we'll have to represent. We'll have to create a continuous pressure difference, delta P. So this such that the volume flow rate, okay, delta V by delta T is directly proportional to this pressure difference and inversely proportional to a property of the system which is called viscous resistance. That is its resistance to flow. Just like electric current flowing through a potential difference through a conductor, the conductor opposes the flow, providing a resistance, or heat flowing through a thermal conductor. So a temperature difference creates heat flow, but the heat flow is opposed by the thermal resistance. So like that over here, this volume flow rate is going to be this pressure difference divided by a factor called the viscous resistance. So Poiseuille's equation actually tells us the relation between the volume flow rate and the pressure difference divided by viscous resistance across a cylinder for this condition, for laminar flow of liquid. Okay, and we'll prove that this viscous resistance comes out to be 8 eta L upon pi r to the power 4, where eta is the coefficient of viscosity of the fluid, L is the length of the pipe, and r is the radius of the pipe. 8 is just a numerical factor. Pi is also just a numerical factor. So viscous resistance is given by this formula. It's a very interesting derivation actually, and we'll also get a relationship for the velocity gradient. We'll see that we'll get like this, that dv by dr is going to be proportionate to minus r. So we get v like this. So it is basically what we call a parabolic velocity profile. It's not a linear velocity profile. It's a parabolic profile. If we draw those vector arrows proportional to the actual velocity, so the shape of that envelope that they form, that will be a paraboloid. The liquid molecules going through the central axis are going at maximum velocity. And as you go radially outwards from the central axis, the velocity decreases such that it parabolically approaches zero as you come to the outer circumference. So the thing is, you will have to, I mean, we'll come to the derivation and logic of these, but you will have to memorize these as facts because there's no way you'll be able to do the derivation of this formula at an exam level or this formula for that matter. Okay, so you have to know how to use these directly. So let's come down to this now. So what we do here is within this cylindrical pipe, we will first consider a cylindrical section of like a cylindrical shell of fluid that is moving across. So we'll first consider that. Okay. So just imagine that we have this thin cylindrical shell of liquid and a small thickness like dr and a radius r. And this shell of liquid is moving at a speed v. Okay, so the shell that's just above it, that is moving at v minus dv, and the shell that's inside it is moving at v plus dv. Okay, so the central line of liquid molecules, they're moving fastest at v naught. Okay, so this is a thin shell of radius r and thickness dr. Okay, and of course length l. So this thin shell, it is moving such that on the shell surface, okay, because the shell is moving faster than the next shell outer to it, so there'll be viscous force acting like this. So there'll be a viscous force which will be equal to the area of the surface into the coefficient of viscosity into the magnitude of the velocity gradient. So area will be 2 pi rl, the outer surface area. This is the viscous force or the drag force on its outer surface. So surface area into coefficient of viscosity into now this velocity gradient, it will have to be, because we're taking mod, we'll have to write it as dv by dt, because mod of dv by dr will be minus dv by dr, because the velocity is actually decreasing with r. Okay. So this will be the viscous force. Okay. Now what is happening? This is moving at a uniform rate. It's moving at v, but its acceleration is 0. So the difference of the difference of the force due to pressure from either side. Here the pressure was PA, this side the pressure was PB. That has to balance this viscous force. So the pressure into area from this side has to be greater than the force due to pressure from this side, so as to maintain this flow at a uniform rate. The acceleration is 0. Okay. So because the acceleration is 0, now we can see that FA minus FB minus the viscous force has to be 0. So this here tells us that the pressure difference into this area will have to be balanced by this. So this will have to be minus 2 pi r L theta into dV by dt. Okay. Don't be bothered by the minus sign because it's actually coming from the mod. So you can also understand it this way, that PA minus PB is equal to 2 pi r, or this r will come here, pi will also cancel. So I'll just leave it this way. So 2 eta L upon r into mod of dV by dr. We'll remove the mod thing later. Okay. So this equation actually shows us that mod of dV by dr is proportional to r, because this pressure difference upon 2 eta L, this is a constant. Okay. So that means minus dV by dr is basically a constant into r, where that constant is this thing, this pressure difference divided by 2 eta L. So when we integrate this, we understand how velocity is varying with position. So at r equal to 0, the velocity is v naught. At r equal to r, let's say the velocity is v. So from this we have this relation that v will be equal to v naught into c, or v naught minus c into r square by 2, this kind of factor. Okay. Now this relation is also such that at r equal to capital R, v should become 0, because just at the inside surface of the pipe, of the cylindrical pipe, the velocity of the liquid should just about be tending to 0. Okay. So from that you can see that c by 2 is actually 1 by r square. And that's how we get this relation that v is equal to v naught into 1 minus r square by r square. So we get the parabolic velocity profile first of all. Now once we get this velocity profile, okay, from this again we can see that, so we'll get the volume rate. Okay, you can just take a bit of time first to go through this section. I'll just take another 5 minutes. Don't think you have another lecture right now, so it should not really bother you. Okay. So I'll just take another 5 minutes after this to complete this section.
So you can just continue and send the PDF out.
Yeah, I'll send the PDF. I'm just saying go through the steps and ask me if there's any doubt. You need not note down all the steps right now. You can just make sure you understand these steps. So far, this is the concept. We have made the free body diagram of that shell, okay, the thin shells FBD, and we are applying the condition that it's moving uniformly. So from that, we are getting this relation that the velocity gradient is proportional to r. Now notice below also we had got a value of c in terms of capital R. So that's also telling me an important relation here. Okay. So this is also telling me that PA minus PB divided by 2 eta L is equal to 2 by r square. This also we'll keep in mind, that in terms of actually this will come out to be V naught upon minus 2. So this pressure difference will come out to be 4 V naught eta L on r square. So now we have to convert this into volume rate. We have got the relationship of pressure difference with respect to the velocity of flow of the central axis. Now for the volume rate, we can denote it with the symbol Q, but basically it is delta V by delta T, that kind of thing. So what is happening is that if you look at the cross section of the pipe, what we understood from the cross section of the pipe is there are cylindrical shells that are moving with different velocities. There's velocity gradient. So taking a thin cylindrical shell like this, so it occupies a certain fraction, differential fraction of the total area of cross section. So this area of cross section that this cylindrical shell has, it is 2 pi r dr, and that cylindrical shell is going into the plane over here with a velocity which we've written above. V is equal to V naught into 1 minus r square by r square. So the volume of liquid flowing through that shell is the velocity of flow into area. So Q will become integration of Vd. So that is integration of V naught into 1 minus r square by r square into 2 pi r dr, from r equal to 0 to r equal to capital R. So given this kind of a velocity gradient or a velocity profile, this is the total volume rate. You're integrating the velocity over the area of cross section. So the volume rate now becomes like this: 2 pi V naught, okay, into integration of r, so that is r square by 2, okay, minus integration of r cube, that is r to the power 4 by 4 r square. And on this you have the limits 0 to capital R. So you can see that this cube becomes 2 pi into V naught into r square by 4. So it becomes pi r square V naught by 2. So this is the volume rate in terms of V naught. And earlier we had seen the pressure difference in terms of V naught. So here we have seen that this V naught is this pressure difference into r square upon 4 eta L. Okay, so now we can eliminate this. So V naught is equal to 2Q upon pi r square, and that is equal to, from above it was this pressure difference into r square upon 4 eta L. So you get that relation, that the volume flow rate is the pressure difference into pi r to the power 4 divided by 8 eta L, or what we write as this pressure difference divided by viscous resistance. So viscous resistance is this factor, 8 eta L divided by pi r to the power 4. Okay. So this is the proof of it. Okay. But the more important thing is the conceptual application over here, that to force a viscous fluid at a certain volume rate, this is the volume rate, through a certain pipe, you have to create this much pressure difference, which is equal to that volume rate you want multiplied by the viscous resistance. And the viscous resistance is something that depends on the dimensions of the pipe, radius and length, and on the viscosity of the liquid. So it depends on those two things. Okay. Whereas in steady flow, we don't need to create pressure difference to make liquid go through at a uniform volume rate through a horizontal pipe, because viscosity is not there, so there's no viscous resistance. So once you set the liquid into motion, it just keeps going at the uniform velocity and uniform rate. You don't have to keep applying a pressure difference to maintain that state of uniform rate of flow. Okay. So anyhow, with this we complete the theory part and the examples and all of properties of matter. So please do complete from your workbook, I mean from your module and from HC Verma. This is not like a chapter which has huge amount of weightage or very difficult questions in JEE. So I think like the module and HC Verma together will provide more than enough examples and questions. The important thing is you should just keep in mind all the small little formulae and tricks of solving and all, so that you can score like nearly 100% of the marks that come from this portion. Okay. So next week we will most probably start simple harmonic motion, unless you have a lot of doubts. Okay. Yeah, Reynolds number is not in syllabus. We will discuss maybe when we are doing the doubts and all, but it's not directly in syllabus. Okay. Okay. So
Can you
right,
send
so
the
next,
PDF on the group?
yeah, I will send the PDF. So, okay, people.
Okay.
So that's it.
Bye.
Okay, wish you all. Yeah.
Sir, I'd send some doubts of gravitation. So will
Okay.
you please help me in that?
Yeah, I will send you some solutions for those. Okay.